Okay, quick update on one of my safe projects here. So I picked up the Sparrow's Vault combination safe. It's a neat way to learn how safes work and learn how to crack them. And a neat thing they do here is they give you different lever arms, kind of different training skill levels. So there's a lot of information about this, but it's pretty interesting. After a few weeks or so, it was a good way to kill some time. And then after that, I figured, well, if I can do it, then maybe a computer can do it. And so then that kind of set me down the track of how do you get electronics and motor and all those things to drive it. But I wanted to try to do it a little bit fancier. So instead of a brute force attack where you're going after every single number, you're actually following the Sparrow's guide, which is how to crack safes. So whenever you buy this, you get this. And inside of that, it has steps on how you figure out each, how you crack the safe, how you figure out where are the gates. So you have these sheets that you go through. And at first, with the simple arms, you can find it pretty quickly. It gets harder when you go to the straight arms, which don't make the gate stand out as much. I found it pretty hard myself. Whenever I went to the harder set point, it was really hard to visually see the indicators between each one of these, because as you get to the higher and higher levels, and you're trying to listen for the arm to fall into the cam, that difference of being inside the gate or not is extremely subtle on the hardest level, on the straight arm. This is a staggered arm that makes it a bit easier to indicate. So to help me there, when I was doing it manually, is I actually used like a little digital angle finder here. So I just stuck that to the front, and that helped give me a little bit more resolution in between each of the markers. So there's 100 markers around here. When I use this little digital angle, it does, of course, 360, but it does another decimal point there. So that gives me a lot more indicators in between each one of these notches, because it's very subtle when you're using the actual arm to try to figure out where the contact point is, and then use that to figure out which gate you're in. So anyways, so doing it manually, I was able to do it in about an hour. I think you could probably go, of course, get that even faster, but it kind of made me wonder, could a device do that? So in searching, there seemed like there were a few devices that did this. The popular ones do just a brute force attack, so they just try every single combination, and that seems to be a good solution to discs that have false gates, because in general you have 3 discs that are in a row with a cam on the back, and then there's a lever arm that falls. When the gates are aligned, that arm can fall down and the cam can grab it and pull it open. I'll show a video of what that looks like if you haven't seen that before. There's a lot going on here. I probably don't want to get into the details of how safes work, but I can show you at least what I mechanically did here. So with the device I have right now, it's basically a large outrunner, like quadcopter motor, just with a adapter to plug right into the front of the safe dial. So so this is ABS printed plastic with an outrunner. There's a little insert here that I printed out of a kind of like rubbery TPU material, and that's just shy, so you can kind of press fit her in like that, and then it has a good grip of it. Then you don't scratch the dial or anything. It kind of stays on there. So you could potentially have different inserts for that. Behind the motor is a couple encoders. For this one, I'm using the ODrive motor controller. It's a really neat controller that I've used on other projects. It basically drives an outrunner like a stepper motor, but it's very smooth and quiet, can give you a lot of torque. It's really neat, for sure. And I have also a little screen, little input on what commands you want to send it. And then the second, the microcontroller that's kind of driving the whole operation here, I'm using the Teensy 4.0. It's really fast. And then the last part is just a little bitty microphone. And there's several different ways to sense when you're inside the gate or not. When I'm manually manipulating the dial, I can feel the resistance, and I can actually feel when I get inside the contact points. And if I'm very, very gentle, I can feel where that contact point is and hear it click. Now, if I go too fast, I can't feel it. If I go just slow enough, I can hear it click and I can sense it. So when I was trying to find the sensors in this is what took about 60-70% of my time, was just how am I going to sense what I can feel with my hands. I can hear it and I can feel it. And the feeling, I felt that was way more obvious than the sound, correlating sound versus I can just stop my hands right when I get to the right point. I can just gently push it just right and feel it stop and say that's the contact point, and then take a reading from my digital meter when I'm using the straight arm, the hardest arm. So initially I thought, well, I'll put a gyro, an accelerometer on the front of this dial through a slip ring, connect it to the front here, and this feeling that I can feel, maybe the gyro would be able to feel it. Well, that was hard. There's a few things that was fighting against me. One is when the motor spins. The motor needs to spin very perfect, because I'm trying to feel a very small subtlety. Also, when it spins, you almost, if you go too slow, the gyros couldn't feel the click that was there, couldn't feel the motion. Then if I went too fast, the gyro didn't have a fast enough update rate through I²C to tell me what the position was. So it was a couple different problems getting in the way here. And so I went after this, taking different approaches to try to make it as fast as possible and make it reliable. So to speed, the first brute force speed approach was to use the Teensy 4.0. So that has a 600 megahertz, like M7 processor, blazing fast. The next problem was I²C. That wasn't as fast as I wanted to go. Generally, I wanted to go at this speed. This is maybe about 40 RPM or so, but you need to have at least a little bit of speed here to get through the 300 different points that you need to go through. That number is, of course, compounded as you go further down the disks, and you need to spin multiple times to get to that point. So Teensy brute force of a processor to go after this, getting away from I²C and going to just an analog microphone. So this is just analog in on the chip. Also, I have these little screens. These are nice little Sparkfun I²C, easy to plug in screens. However, just interacting with them, and even interacting with the motor controller, which uses a UART interface, was too slow. So I had to kind of clean up the code a little bit too, so that whenever I go to listen for that contact point, that I'm doing nothing else. So kind of what happens here is whenever I go to a dial position, I need to go find the contact points. What I do is I tell the motor to go to, let's say, go to a point past the contact points, and then I go into a loop where the only thing I'm doing is listening for, I'm tracking the position that the motor is in, listening to the microphone, and then the only math operation there is the microphone at a certain threshold that you can hear the click, and when the click happens. So whenever it does the spin, it's listening for the click, and then when it hears the click, and there's actually 2 clicks in here, when it hears the click within each one of these ranges, it then saves that as a variable of what the magnitude of the click was and the dial reading when it heard it. So then that will allow you to collect information on that one dial point. So you do that 100 times, and then you will take the best of all of those, and then you can create basically what the solution is for that combination for one of the disks. So the first disk that you need to find, it's actually the third disk, but it's the easiest one to find, and by hand you can find this one really quickly. You just kind of have to nudge it along. That only takes, if you're trying every 100 combinations, it's about 2.5 minutes. If you're skipping by twos, the Sparrows actually skips by 2.5. That's what they recommend. So do it by 2.5, takes 1.5 minutes. It's very, very quick to check all those. It gets a lot harder when you go into the second disk and then the third disk. The second disk, you have to first set one of the disks. You have to first check a dial, go to the known dial, then check the cam. Then at that point you have to reset the whole switch again and then try it all again. So if you're doing the full 100, that takes about 20 minutes to go through. If you're skipping, of course, the time is just in half, about 10 minutes. And then the last disc is more like the second one, but there you don't need to do any measurements on the final one. The final one, you'll just fall into the gate and the safe will open, and that's obviously the most rewarding part about it. I think the funnest part about all these safe cracking lock picking is it's sort of like a puzzle. It's a well-established puzzle, which is lock picking, and whenever you the reward of solving it is pretty awesome, especially with this safe. Just for the experience of finding that unknown number and feeling it click in is really neat, really exciting. To physically find, and of course having the computer do it is pretty cool too. To basically hide that information from the computer, let it determine what it is, and then go for it. So I have some clips of that I'll share. I'll do like a speed up 40 minutes, so I'll just have that run quickly, maybe slow down in a few moments to show you whenever the screen is reporting what dial that we're in, the next dials that it's checking, and then whenever it actually unlocks it. So yeah, that was just basically a program status update. Leave in the comments below if you're interested in this project, if I could share anything with you. Yeah, thanks for watching again. And again, shout out to the Sparrow's Vault, good little product, T-Motor U8, ODrive controller, Sparkfun, Teensy 4.0 microphone, and all these little parts. This was just basically my little hobby project to keep me sane, give me something to do here. So. Oh, that's it. Oh, okay.